In 2005, ID Software released the source code to one of the most influential video games ever made, Quake III Arena. Programmers dug through it, and buried deep inside, they found this: a small function to compute 1 over the square root of a number. But look at the middle, a constant that seems to come from nowhere, 0.05F3759DF. A bit shift, a subtraction, and right beside it, a comment left by whoever wrote it. What the heck? Even the author didn't explain it. This tiny function computed 1 over a square root about 4 times faster than the normal way. Fast enough to help draw whole 3D worlds in real time. And for years, no one could say who wrote it, or why that magic number works. Today we decode it, bit by bit. And by the end, that line won't look like black magic. It'll look like one of the most beautiful tricks in all of programming. First, why would anyone need this so badly? The answer is light. To make a 3D surface look lit, the engine needs to know which way every tiny facet is facing. It's normal, as an arrow of length exactly 1, a unit vector. But the arrows you compute come out at every length. To fix one, you divide the vector by its own length. And the length of a vector is the square root of x squared plus y squared plus z squared. So to light a single point, you need 1 over a square root. Now multiply that by millions of points, dozens of times a second, on 1999 hardware, where the square root was one of the slowest things the processor could do. It was the bottleneck between you and a smooth frame. Make 1 over a square root fast, and you make the entire world move. To understand the trick, we have to understand how a computer stores a number with a decimal point, a float. A 32-bit float is just 32 ones and zeros, split into 3 parts. 1 bit for the sign, 8 bits for an exponent, and 23 bits for the mantissa, the fraction. The value it represents is 1 point something times 2 to a power. The mantissa gives the 1 point something, a number between 1 and 2. The exponent slides the point, scaling by powers of 2. It's scientific notation in binary. Now the move that starts everything. Those same 32 bits, you can refuse to read them as a float, and instead read them as a plain integer. Same bits, different interpretation. Stop treating this as a decimal number, treat it as a whole number. The question is, what whole number do you get? Let's compute that integer. If the exponent bits hold e and the mantissa bits hold big M, then reading all the bits as an integer gives, essentially, e times 2 to the 23 plus m. Now compare that to the logarithm, base 2, of the float's actual value. The value is 1 plus little m times 2 to the e minus 127, where little m is the fraction between 0 and 1. Take log base 2, you get e minus 127 plus log 2 of 1 plus little m. And here's the magic. For little m between 0 and 1, log 2 of 1 plus m is almost exactly equal to m. A straight line with only a gentle bend. So the log is approximately e minus 127 plus m. Look at the two expressions. The integer from the bits, divided by 2 to the 23, is e plus little m. The logarithm is e plus little m minus 127. They're the same thing, up to a scale and a shift. The integer you get by reading a float's raw bits is the base 2 logarithm of that float. Every floating point number carries its own logarithm hidden in its bits. The hardware never intended it. It falls out of the format for free. Now the payoff. We don't want the logarithm for its own sake. We want 1 over the square root. And in the world of logs, that operation becomes almost trivial. 1 over the square root of x is x to the power minus 1/2. And the log of x to a power is just that power, times the log. So the log of 1 over root x equals minus 1/2 times the log of x. Negate and halve. That's the whole operation in log space. But we just learned a float's bits already are its log, so we can do it directly on the integer. Halving a number is a single right bit shift. I shifted right by 1. And negating, then shifting everything back into place, accounting for that 127 bias and the small correction, collapses into one constant we subtract from. Work out what that constant must be. And it comes to 1,597,463,007. In hexadecimal, 0.5F3759DF. There it is. The magic number was never magic. It's 3 halves times 2 to the 23 times 127 minus a tiny correction, the exact offset that makes negate and halve the logarithm land on the right bits. The shift halves the log. The constant negates it and fixes the bias. One subtraction and you've computed 1 over a square root without ever taking a square root. But it's not perfect. That straight line approximation of the log leaves a small error. The first guess is off by up to about 3%. Impressive, but not smooth enough for lighting. So the code does one more thing. A single step of Newton's method, the classic technique that takes a rough guess at an answer and sharpens it, roughly doubling the correct digits each pass. Feed our clever first guess into 1 Newton step, and the error collapses from a few percent to a fraction of a percent. 1 iteration, essentially exact. Guess with a logarithm trick. Polish with Newton. Done. And who wrote it? For years, nobody knew. The trail ran from ID Software, back through a graphics company called 3DFX, to Silicon Graphics, and the constant itself has been traced toward the legendary numerical analysts William Kahan and Cleve Moeller. The comment in the code suggests even the programmers who inherited it were as mystified as we are. And the kicker, the famous constant isn't even optimal. A researcher named Chris Lomont later found a slightly better one. The line everyone worships is a touch wrong, and it still rendered the worlds of an entire generation of games. So that's the whole secret. It looks like someone mashed the keyboard and summoned something dark, but every piece has a reason. Square roots were slow and lighting needed millions of them. Floating point numbers, by an accident of their design, carry their own logarithm in their bits. And in the language of logarithms, a square root is just a halving, 1 shift and 1 subtraction. A line that looks impossible becomes, once you see the logarithm hiding inside every float, almost inevitable. That's the thing about the best tricks in programming. They're never really magic. They're a beautiful idea, hiding in plain sight, waiting for someone to write what the heck and figure out why it works.